Hello students, so in this video I'll be discussing about the derivation of the three equations of motions. But before going for derivation of the three equations of motion, let us try to understand one more thing, that is what is represented by the area under velocity time graph. So we have drawn different types of velocity time graph. In our earlier video we have learned that. And we know that velocity by time is acceleration. So the graph line will indicate acceleration. Here what we are trying to describe is, if we calculate the area under the graph line for a velocity time graph, what will we derive? So here we have drawn a graph representing a body which is moving with a constant velocity. Let's say the velocity is v, and we consider 2 points from A to B. So at point A let the time be t1, and at point B let the time be t2. So the time gap will be t2 minus t1, that we consider it to be t seconds. Okay. So area under the graph from A to B, that is the area of this shaded portion. Now if you look at the shape, it is the shape of a rectangle, or you can say square, side into side. To get the area we have to apply that formula. So whenever you do any kind of derivation in physics, since you are new to derivations in class 9, you always have to draw a diagram, and after drawing the diagram you have to write what you have actually considered. So what you have assumed. So I have written whatever is there in the diagram, I have written here. Let us consider a body to be moving with constant velocity v between time t1 to t2. Let the time interval be t2 minus t1, that is t seconds. So now what we will calculate? Area under the graph AB. So under that how much area is there? So area under the graph AB, it will be what? Area of AB, this point I marked as C and this as D. So ABCD. So ABCD looks like a rectangle. So side into side or length into breadth, whatever you say. So area of ABCD will be AD into AB. So what is AD? AD, as we can see from the graph line, this is velocity. And what is AB? AB is similar to DC, and what is DC? It is the time interval t. So t2 minus t1. So t2 minus t1 is t. So v into t. So we know that velocity is distance by time. So if we take time this side, it becomes v into t gives you s. So from this we can replace v into t. Instead of v into t we can write what? S. So area under the velocity time graph, it gives us what? It gives us the distance traveled by a body. So it can be any kind of velocity time graph. Suppose your velocity time graph is of this shape and you are supposed to find out the distance traveled. So what you will do? You will calculate the area under the velocity time graph. You will use the formula of triangle. Similarly, if suppose the velocity time graph is like this, the difference between these two on both sides, if we take velocity, difference between these two graphs is that here the body is starting from initial velocity 0. Here the initial velocity of the body is not 0. So here also if we have to calculate the distance traveled, we have to calculate the area under the graph, then we have to, the shape becomes that of a trapezium, we'll use that formula. So whatever is the shape which comes under the velocity time graph, if you calculate the area under that graph, you will end up getting what? Distance traveled by the body. So the graph line gives us acceleration for a velocity time graph. The graph line will give us acceleration, and area under the graph will give us the distance traveled by the body. Next, we come to the derivation of the three equations of motion. So there is a graphical derivation. So you have to derive it from a velocity time graph. So for this we consider this situation. What is the situation? Let us consider a body with initial velocity AO. So from the graph we have drawn a graph line A to B. It is a uniformly accelerating body. So the initial velocity is AO. So let us consider the body with initial velocity AO. It accelerates uniformly since it's we have drawn a straight line. So it's uniform acceleration, and after time interval OC. So I have marked this as O, this as C. So after time OC, the velocity of the body, final velocity, it will become BC. So BC we have marked it as V. So you see here Another thing that we have to consider here or understand here, AO, there is a rectangle. If you look at this dotted line, there is a rectangle. So AO will be equal to DC. And what will be the value of DC? It will be U, because AO is equal to DC. AO is U, so DC will be U. So this whole thing is V. This is U. So whole thing is V, this is U. So the remaining portion, that is from B to D, that will be V minus U. So that is what we have written here. Whatever we have considered here, we have written here. So for all the three equations, we will be using this graph. So every time you don't have to draw the graph, drawing once and writing once what you have considered will do. So the first graph, it is called the velocity time relation. Now one important thing is that all the three equations, you have to remember it by their specific names. They have specific names. Many a times we don't call them first equation, second equation, third equation. We call them by their name. So the first equation of motion is velocity time relation. So relation between velocity and time, it is acceleration. So we take the definition of acceleration. If you recall, acceleration of the body is equal to rate of change of velocity. So rate of change of velocity means change of velocity with respect to time. Instead of rate, we have written time. Change of velocity means final velocity minus initial velocity by time. So it is exactly the same way that we derived the formula for acceleration in our earlier video while explaining acceleration, I told you. But difference is that here we'll first put the variables from the graph, then we'll put the other variables. So final velocity is BC, so I've written BC. Initial velocity is AO, so I've written AO. And the time interval is OC. After that, what I am doing here, I have replaced it with the variables like A, it was final velocity BC, so BC is V, then initial velocity AO, AO is U, then divided by time OC, that was T. So now we simply reshuffle to get the form of the equation. So T we take here, so it becomes AT is equal to V minus U. We leave the V here and take U this side, so minus U will become plus U. So it becomes V is equal to U plus AT. So this is the first equation of motion or velocity time relation. Next is position time relation. So position time relation is the second equation of motion. Position means where the body is from you. That means the distance. So you can also call it distance time relation. So for this you have to calculate distance traveled. So from a velocity time graph, how can you calculate the distance traveled? You have to calculate the area under the graph. So it will be area under the graph AOCB or ABCO. So what is this shape like? This entire shape is that of a trapezium. So I have written here distance traveled is area under the graph AB. So what is area under the graph AB? It is area of trapezium AOCB. So area, this trapezium, now if you see here, this trapezium can be easily divided into a rectangle ADCO or AOCD and a triangle ADB. So that is what we have done here. Area of trapezium AOCB, so that we have broken into area of rectangle AOCD plus area of triangle ADB. So to get the form of the equation, we have done that. So S is equal to AO into OC, rectangle. Rectangle is what? AO into OC. So that we have written here AO into OC, and triangle, it is a right angle triangle, so half into AD into BD. So half into AD into BD. Now AO is nothing but initial velocity. If you look at the graph, OC, so let me focus both, it will be easy for you. So more or less we can now follow both the things. So when we are talking about, so area of rectangle AOCD, so that will be AO into OC, area of triangle ADB, that is half into AD into BD. So what is AO? AO is nothing but the initial velocity, then OC is T. So we have written here U into T plus half into, so instead of AD, I have written OC here. Why? Because AD is same as that of OC. So AO half into OC into BD. Now we replace the variable. What are the variables we are having here? You see, S is equal to ut plus half. OC, in place of OC I have written t, and BD is if you look at the diagram, you'll know it is v minus u. Now v minus u, these are velocity, but here it is a position time relation, so we'll try to bring in more time as possible. So from the first equation, what we'll do here, v is equal to u plus at that we have got. Now we'll exchange so that we can replace this v minus u. So I take the u this side, it becomes v minus u is equal to at. So instead of v minus u, I can write at here. So S is equal to ut plus half t into at. T into t is square. So ultimately the equation becomes S is equal to ut plus half at square. This is the second equation of motion. Third equation, the same thing we'll do. It is called position velocity relation. So it is a relationship between distance and velocity. So again we'll calculate the distance from the graph that we have considered. So distance traveled is area under the trapezium AOCB. So distance traveled is represented by S. So here we'll take the formula of the entire trapezium. So half into base into sum of parallel side. So half into the base, if you recall the diagram here, the base was what? OC. So we have taken the base as OC and sum of parallel sides. These two are parallel side. So BC plus AO. So BC plus AO. So S is equal to half into OC was T. OC was T and BC was V and AO was U. So V plus U. Now this time we will replace with the help of the first equation because it is a distance and relationship between distance and velocity. So we'll try to bring in more velocity here. So S is equal to half into, now how will you replace time? Again from the first equation, on the side you will write V is equal to U plus at. So U we take this side, so V minus U is equal to at. So you leave the, we are replacing T, so you leave T here and take A. So A will come down, so it becomes T is equal to V minus U by A. So instead of T, we are writing this whole thing, V minus U by A. So S is equal to, below in the denominator we have twice A. On top we have V minus U and this side V plus U. Now this is of the equation A plus B into A minus B. So we can simplify it and write twice AS. This twice A we take this side, twice AS, and it is A square minus B square. So instead of A we have V here, so it will be V square minus U square. So this is the third equation of motion. Twice AS is equal to V square minus U square. In some books you will also find it written as V square is equal to U square plus twice AS is the same thing. If you take twice U square this side, this minus will become plus. So you can write it as U square plus twice AS is equal to V square. This also is possible. So these are the three equations of motion and their derivation from this particular graph. So whenever you derive any equation, first you have to draw this graph, write the description below, and then you have to derive the respective equation. Thank you.